Okay, now we continue with subchapter 3.5, where we are going to talk about the additional equations for turbulent flow. Before this, we already talked about laminar flow, which can be described by the continuity and momentum equations. So turbulent flow requires some additional equations, so the basic of the equations still requires continuity and momentum equations, just like what laminar flow has in its governing equations, but there are some additional equations to cater the turbulent flow. It is known that small disturbances associated with disturbances in the fluid streamlines of a laminar flow can cause the flow to become chaotic and random. That is what turbulent condition is. Turbulence may be induced by the surface roughness. When the surface is rough, basically it will create this small scale vertical structure in the flow, and these small structures causes the flow to become chaotic. The onset of turbulence depends on the ratio of inertial force to viscous force, which is also known as Reynolds number. So as we know that for laminar flow, Reynolds number is small, which means that the viscous force is high with respect to inertial force. Meanwhile, for turbulence flow, Reynolds number is high, which means that the other way around, this inertial force is higher compared to viscous force. I think the easiest analogy that we can use to describe this is, as we know that laminar is highly ordered flow, meanwhile turbulent is highly disordered flow, which is hard to control, and laminar is highly ordered and easy to be predicted because it is very organized. So it's like when you drive a car, when you have this acceleration pedal and brake pedal. So when you push the brake pedal, it's like increasing the viscous force, because viscous creating resistance in the flow. Okay? The higher the viscous, the higher the resistance, which is the harder for the flow to deform. So it's like braking effect. Like if you brake your car, it will be easier for you to handle, to steer your car, which means that it is in order. But when you accelerate your car, you push the throttle. So what is going to happen is you increase the velocity. By increasing the velocity of your vehicle, it's like you increasing the inertia. So when the inertia is high, it will be harder for you to control the car, and the tendency for it to become chaotic and move randomly is high. So actually it's quite similar to fluid flow as well. If the inertia is high, it is turbulent. If it is high, it will be hard to be controlled and it can become chaotic and random. Meanwhile, if the viscous force is high, the flow is more organized and easy to handle. Okay, this figure shows the velocity fluctuating with time at one particular point in a turbulent flow. So as you can see that with respect to time, this U prime t represents the small fluctuations, where you can see that it is very random and it fluctuates quite a lot, and it fluctuates around this U mean. So the velocity can be decomposed into a steady mean value U bar. So U here is the mean, so this line is the U mean, and this U prime t, it fluctuates around here. So the superimpose of U prime t onto U mean, you will get this U. So this is your ut, u as a function of time, and this is the u mean and plus the u prime t. And these fluctuations not only happen to u. For momentum equation, actually it affects u, v, w, and the pressure. And if we involve energy equation, it will affect the t as well. So there's a fluctuation in temperature as well. If you look at the previous researches on turbulent flows, you can see a lot of visualizations that reveal rotational flow structures, which is called as turbulent eddies. This is an induced turbulence with a wide range of length and velocity scales, which is called as turbulence scales. So when there is a wide range, it covers a very small scale until quite significant scale, where the largest turbulent eddies have a characteristic velocity and characteristic length of the same order as the velocity and length scale of the mean flow. Okay, when it is in the same order of the velocity and length scale of the mean flow, which is mean flow is the one that you can see in lamina. So since the eddies, the induced turbulent is very significant, it cannot be neglected. If it is very small, we can just neglect it. But since it is at the same order, so it is significant. It can be seen. It does affect the whole flow. This is an example of like a typical flow domain which has a cross-sectional area of 0.1 meter by 0.1 meter with Reynolds number which is quite high, where you might have turbulent flow that contains eddies down to a very small size, 10 to 100 millimeter. For us to do simulation on turbulent flow, we need to make sure that the mesh that we build is very fine so that we can capture it, because as it's mentioned that the range of the characteristic length is very wide, where it can be very small until very big. So to make sure that we do not miss, or we could capture all of the vertical structure from the small until big, we need to make sure that the mesh is very fine. And same goes to the time steps, because the velocity, as we know that velocity is as a function of time. So since if the velocity has a very high range, we need to make sure that the time step is very small so that we can capture all the vertical, all the small vortices that is induced due to the turbulence. In this slide, we are going to start to discuss on one of the commonly used turbulence model, which is the K epsilon two equation turbulence model, where this model uses Reynolds average Navier-Stokes or RANS equations. Okay, as you can see, actually for turbulence model, it is similar to lamina, where it uses continuity equations, as you can see at the upper box, at the top box here. This is continuity equations, where we have seen this in lamina before. And as in the next box here, you can see at the 3.31 here, this is actually momentum equations for x component, and 3.32 is momentum equations in y component, and 3.33 is the energy equations, where it has temperature. So this equations is for two-dimensional. Okay, if you see here, most of the terms are very familiar as we have seen in lamina, except it has several additional terms here. We have u prime, v prime, and t prime here. So the difference between regular Navier-Stokes equations that we use for lamina and the Reynolds average Navier-Stokes equations is actually the turbulence fluctuating terms. Yeah. There are several equations quite important to be understood in this, where this is to solve the mean of the rates of deformations, okay, and also just to find the mu t, which is the eddy viscosity. This is the viscosity that is induced due to the turbulence, and also k here is the turbulent kinetic energy. Okay, the turbulence transport of temperature is taken to be proportional to the gradient of the mean value of the transported quantity, and here this symbol is represents the turbulent diffusivity. And the bottom one is called as a turbulent Prandtl number, where Prandtl number generally known as the ratio of the momentum diffusivity to thermal diffusivity. And the turbulent kinetic energy, as you know, that kinetic energy is equal to half v squared, and this is the rate of dissipation of turbulent energy, which is epsilon. So actually this is the k and epsilons comes from the k epsilons to equations turbulence model. It requires to have these two, and from the local values of k and e, which is the rate of dissipation of turbulent energy, A local turbulent viscosity can be evaluated. Okay, so actually the effect of this turbulent kinetic energy and the rate of dissipation actually is induce viscosity. So there will be an additional viscosity in the flow, which may affect the flow structure. Yeah, after several like derivations, this is the final form of this K epsilon to equation turbulence model. And the top one is the continuity equations, and then we have this momentum equations, and the bottom one is the energy equations. Okay, take this example 3.8. So we consider the two-dimensional CFD case of the flow between two stationary parallel plates. So to demonstrate laminar and turbulent nature of the fluid flow. So by using CFD with the dimensions of h is equal to 0.1 and length equals to 10 meters, observe the velocity and viscosity profiles in the fully developed region with the working fluid taken as air, density equals to 1.2 kg per meter cubic, and dynamic viscosity mu equals to 2 times 10 power of minus 5 kg per meter seconds. For inlet velocity of u equal to 0.02 and another inlet velocity equals to 1. So I believe that this u in 0.02 will give you laminar flow and 1 will give you turbulent flow, because it is higher. The Reynolds number for this case is higher. So this is the problem setup. Is we have two parallel flow, and then we have a uniform velocity enters from the inlet, and then we can expect velocity profile for laminar and turbulence. Okay, this is for two different cases. See, it's not from the same cases. Okay, this is how the left velocity profile is what we can expect from laminar velocity profile, and the turbulent velocity profile will look like the one on the right. Okay, this is how actually it looks like, the developed velocity profile. So as you can see that actually this is the Reynolds number is equals to density times velocity times the characteristic length. For this case is the inlet height over the dynamic viscosity. And then from this Reynolds number, you can get that this 120 is low, and this actually is laminar, and this is for Reynolds number 6000 is turbulent flow. So what we can observe here, we can see that it has a different type of profile between this laminar and turbulent. So what you can see, turbulent velocity profile is more blunt due to the high viscosity, and the turbulent flow has a much steeper velocity gradient near the wall. So you can see that actually the area under the graph is similar for this case, because this is a normalized velocity, okay, u over u inlet, uniform inlet. So that's why it looks like this, but actually in the real case it's not necessarily need to be this like this. This is because it is normalized, so it make us like easier to compare what is the effect of a Reynolds number onto this, because changing Reynolds number is not necessarily means that you need to change the velocity. You can change the Reynolds number by changing all these parameters as well, the inlet height or the viscosity. Okay, so it would be best if we analyze it using non-dimensional parameter. This is the viscosity, the dynamic viscosity in the flow as a function of height. So as we can see that actually for laminar, the viscosity is always constant anywhere in the flow, but not for turbulent. Okay, as we seen from the previous all the equations before, there is an induced viscosity, or is also called as a turbulent viscosity, which is due to the K and E. If you look back into the equations here, okay, look back at the equations, this is mu T, this is the turbulent viscosity. So the difference between this temperature di laminar, this is the mean viscosity when there is no turbulent, and then this is the turbulent. the viscosity increased, especially at the center line. So zeros and 0.1 is the wall, 0.1 are the wall, is at the center line, the center of the domain. So it is the most viscous at the center. Okay, this is how the kinetic energy, K profile, and dissipation rate. Okay, these two figures shows the one on the left, it shows the kinetic energy K profile for the turbulent flow in the fully developed regions, and the one on the right is the dissipation rate of energy profile for the turbulent flow in the fully developed regions. As you can see on the left, the kinetic energy near the wall actually is very high. So as we know that the turbulence can be caused by the surface roughness. Okay, for this case, we take it the reason, the source of the turbulence is the surface roughness, where at the source, at the surface, there will be a lot of small vertical structures will appear due to the roughness of the surface, and all these vertical structures creates kinetic energy. Okay, meanwhile, the one on the right, it shows the dissipation rates, epsilon profile for the turbulent flow, and the dissipations of this kinetic energy causes the energy converted from the form of kinetic into heat. So you can expect that the effect of this, although the kinetic energy here is high, the rate of dissipation here is very high at the same time. Okay, so if you remember the equations before this, the mu t here is the ratio of K over epsilon. So when epsilon is very high compared to K, that means that the viscosity here is low. Okay, mu proportional to the K squared over epsilon. So here epsilon is very high. Hence, that's why we have this small mu t compared to the one at the center. As it goes towards the center line of the channel, so you can see that the kinetic energy is reducing. Same goes to the dissipation rates. But still, if we look at this, the ratio, the kinetic energy still has quite some significant value. Meanwhile, the dissipation rates at the center, near the center line of the channel, is very small. So basically the ratio of K power of 2 over epsilon, which will give you this mu t, is significant at this point. So that's the reason why we have this high viscosity. Okay, this profile, viscosity profile, actually explains very well why we have a blunt shape of velocity profile for turbulent. It is because the viscosity, the viscous effect causes the flow to have some resistance to move. It resists to makes the flow much harder to move. It's like a braking, like a resistance. So that's why we have a more blunt shape compared to lamina, because lamina, the viscosity is always constant anywhere in the flow, but not turbulent flow. The viscosity for turbulent depends on the kinetic energy, and also depends on the dissipation rate. So there's a K and epsilon. That's why K and epsilon needs to be calculated for turbulent in order to measure, to compute mu t, and then from there you can get the whole flow structure of turbulence.